So when we represent terms with binding, like here's a simple program in the lambda calculus. It takes two arguments and adds them together. The most annoying operation that we have to think about and deal with is substitution. So here's the classical example of what goes wrong. We're calling this lambda function, and we're substituting in this variable y, and y is the same name as one of the names that we are using inside this lambda. And we substitute it, and we just ruin everything by substituting it into this mess, which does something entirely different from what it was that the program was originally supposed to do. What we're actually supposed to do instead is somehow pick a new name, get this program instead, which does do the right thing, where we have chosen a new name, which is some name z, which is not equal to y. So this thing in bold off to the side, that we must pick the new z to be not equal to y, or generally we must pick the new z not to be free in the thing that we're substituting in, this is called a freshness side condition. This talk is about freshness side conditions. They are the bane of the life of anyone who tries to prove anything about lambda calculus, syntax, or binding, and we'd like to get rid of them, as much of them as possible. So this is a long-studied problem. These freshness side conditions have been annoying many researchers for many years. So there's been a couple of good ideas on how to get rid of them, or at least reduce their number. The first one is to use separate syntactic classes for the free names and the bound names. So here we've got a little hat over all of the names which are bound variables, and we don't over all the names which are free variables. And then we have this nice property that all of the binders bind things in the bound variable category, so that when we're substituting in something that mentions things in the free variable category, we don't have to worry about them being captured. We can just substitute y in fairly blindly there and not worry that it's going to collide with some binders, because the binders all bind things which aren't y. So the next good idea is, well, when we do it like this, we still have to pick names for all of these bound variables. If we're trying to show that two different programs produce the same output, like the same bit of syntax as output, then we still have to worry about, oh, they produced the same, but it wasn't quite the same because they chose different names for the bound variables. So the next good idea is to use numbers rather than names for the bound variables. So there's a minor technical note here. I'm using what are called Bruijn levels, which means the numbers that I'm giving, I'm counting the outermost binder is called 0, and the numbers go up when you call about further innermost binders. If people have seen this sort of thing before, it's equally likely that they've seen them the other way around, which are called Bruijn indices, where the innermost binder is called 0. So it's all fairly symmetrical. There's some reasons why this one is more convenient here, but you could do it the other way just as well. But something to bear in mind if all of the numbers look a bit wrong. So actually, in particular, this is a representation called the locally nameless style, where you're using string names for the free variables and numbers for the bound variables. It's appeared a bunch of times. I think it was used in early implementations of Paulson's Isabelle and Tourette's constructive engine. I'm told it showed up there, but a really good exposition of it is Arthur Chago's more recent paper. So the basic operations that you get when you're dealing with syntax in this style are the things for turning a free variable into a bound variable when we're looking into a binder or coming out of one. So these are operations called open and close. So if we have a lambda here and we choose to open it, we're trying to look at the thing that it binds, we have to give it a name, we call it x, and then all of the bound variables, all of their numbers go down by 1 because there's no longer a 0, and all of the occurrences of 0 get replaced with x. And similarly, there's a closed operation that goes the other way around. And these act fairly straightforwardly on variables. Open with x maps 0 to x, and all of the bound variables go down by 1, and all of the free variables stay as they are. And closed is the opposite. It maps x to 0, all of the other bound variables go back up by 1, and the free variables stay as they are. So this is how, in the locally nameless style, this is how we operate on syntax. When we want to examine a lambda term, we open it. When we're done with it, we're trying to construct one, we close it back up again. So you might expect that if I open it, think, actually, this is fine, I'm not going to do anything with it, and then I close it back up again, I should get back the original term. I would expect that close of open of t is equal to t. However, this is not actually true. This is true only under a freshness side condition. If there were other uses of the free variable x already in T, then when we opened the bound variable, the 0 became x, and now we've mixed up the x's that were already there with the x's that we just opened. And when we close it again, we capture both the things that we'd opened and all of any other occurrences of x that happen to be lying around. So we need this freshness side condition to actually ensure that we don't capture things that we're not supposed to capture. So we've got a trick for getting around this particular freshness side condition. It's called shifted names. It is very, very easy. We should put numbers in the free variables as well. Thank you. Questions? So here we allow multiple things called y, which are in scope, and y0 is going to refer to the first one. But there may be other y's which have been shadowed by this thing. There may be other variables with the same name, and we'll allow that. We're just going to use numbers to disambiguate which y that we're referring to. So this is not a particularly complicated idea. It's not even a particularly new one. It's more or less present in Dan Lyon's COCA language, which is using it for algebraic effects. And Biernicke's work on algebraic effects, where to deal with the problem of possibly having multiple effects which have the same name, then if they have the same name, you can use this shift operator to skip one of them. So we only have to worry about distinct names for different things. So in this style, let's look at what open and close start looking like. So here, they do the same thing on bound and free variables, but if there's another occurrence of x, the variable that if we're opening x and there's already an occurrence of x, then its index, the subscript, moves up by 1. And that means we don't confuse x's that were already there with x's that we're newly opening. And then in the other way, when we're closing them, if we only bind the x0, all of the xi plus 1s just move down by 1. So with this definition of open and close, then in fact both of these equations are actually true, not true under a freshness side condition, just true. And we can define more derived operations in terms of these. Actually, sorry, before that, we've got two more operations that are useful here. We've got weakening, which is to weakening, which inserts a new binder. So we increase the levels of each bound variable, so there's a new bound variable that's not being used. And bind, which is to substitute the 0, the first bound variable, for a particular term. So in the locally nameless style, weak is often left implicit, because if you're using de Bruijn indices rather than de Bruijn levels, you can kind of ignore it and nothing particularly breaks. And bind is often confused with open, that they're both kind of opening a binder and putting something in. But I really want to emphasize that this is a different operation. If I open with x, I'm saying there's a new variable called x. Any other things previously called x should be shifted out of the way. If I'm binding with a term u that happens to be x, then this is like applying a lambda to a variable. I'm saying I want to use this variable that I already have. That's the one that I should be substituting in. So between weak and bind, there's also an equation. If I use weak to get a variable that I'm not using, and then I use bind to substitute it away, this is how weak and bind operate. They just operate on the bound variables. But if I'm using weak to introduce a new variable and bind to substitute it away, then nothing happens. And again, this is not true under certain freshness side conditions. It is just true. So that means we have 4 basic operations. There's open, that reduces the number of bound variables by turning them into one into a free variable. Close, which does the opposite, increasing the number of bound variables. So I'm writing term v for a term which is v bound variables. Weaken, which increases the number of bound variables by just introducing one. And bind, which reduces the number of bound variables by substituting one away. So these 4 operations give you essentially a zipper structure for walking over terms. We've got open and close for moving in and moving out of binders, and we've got weaken for inserting a new binder, and we've got bind for removing a binder. And we've got these 3 basic equations about them. If I move in and then move out, or move out and then move in, then nothing has changed. And if I insert something and then immediately delete it, then also nothing has changed. So from these, we can build various derived operations. So we can rename the variable x to the variable y. That's just we close x, take all the occurrences of x, make them be variable 0, and then we open it up again as with a different name. So here is a thing that we might expect to be true about renaming. If I rename x to y, and then I rename y to z, then that should be more or less the same as just renaming x to z. And normally, if we were not using shifted names, then this is another one of those statements which is only true under a freshness side condition, because what if I rename x to y and y is otherwise already used in the term, and then I rename y to z and I pick up those uses as well? But with shifted names, this is actually just true, because if I rename x to y, any other occurrences of y get shifted up by 1, and then when I rename y to z, they get shifted back down by 1, so nothing happens to the occurrences of y. In fact, the proof that this is true is very straightforward. We just expand the definitions of both sides. That's close x, open y, close y, open z, and we know that opening and then closing y doesn't do anything, so that's close x, open z, which is what we have on the right-hand side. There's other derived operations. There's substitution, where we close something and then bind it. And bear in mind, for the same reason that bind is not open, this substituting y for x is not the same as renaming y for x. But similarly, we'll have relations like if I were to rename x to y and then substitute u for y, then by exactly the same reasoning, that's the same as just substituting u directly. And there's also shifting, which is weakening and then opening something. And this means this gets you a term in which x does not occur. If I shift x in a term t, then there's no occurrence of x0 in t, because all of the occurrences of x0 have been moved up to x1, and there were no occurrences of 0 in weaken, so we end up with a term that doesn't occur. And this is an excellent way of getting rid of freshness side constraints. Instead of talking about a term t in which x does not occur as the hypothesis, I just say a term of the form shift xt. We can also do parallel operations. I can close a load of variables, then open the same number of variables with different names, and this is a parallel renaming. Or if I close a load of variables, then bind them with different terms, this is a parallel substitution. Or I can do this multiple shifting operation, where I can talk about a set of things which are not free in a term. So this is all formalized in Coq, and it's all honestly easy, which is surprising. So one of the things that's formalized is a simply typed lambda calculus. And in the simply typed lambda calculus, when you're dealing with names, one thing that you might want to prove is this equivariance lemma that says, basically, if a term is well typed with a variable called x, then it's still well typed if I change the name of that variable to y. And again, this is another thing which you would normally expect has to have a freshness side condition, because, well, what if there were other uses of x and y, and then I'm mixing those up with the x's that I originally had? But with shifted names, this is again just true without any side conditions, because if we look carefully, suppose that there was an occurrence of y in gamma, and suppose that there was some y free in E. So E will contain a y0, which will be referring to the y in gamma. Then when we rename x to y, x0 becomes y0, but y0 will become y1. So the occurrence of y in gamma is now shadowed by that y to the right. So what it used to be referred to as y0, it's now referred to as, sorry, it used to be referred to as y0, it's now referred to as y1. So this equation is still true, even if there are one or even many occurrences of both x and y in gamma. In fact, we have a general substitution lemma, which says if a term is typable, and for every variable in gamma, applying rho to that variable gives us something typable under delta. So rho is one of those balanced collections of close and weak, and then bind and open. So it's a balanced collection of things which introduces and then removes the same number of bound variables. So it's any mixture of substitution, renaming, or shifting of things. So this is one result, and which has a straightforward proof, which even Coq agrees is a straightforward proof. And it simultaneously is the weakening lemma, the equivariance lemma, the substitution lemma, the parallel weakening, parallel renaming, and parallel substitution lemmas. So yeah, as an example of like my repeated claims that this is in fact easy in Coq, so here is a thing that's reasonably straightforward on paper and mildly annoying, which might even be legible now. This is a CPS conversion, the untyped lambda calculus CPS, with some syntax where I'm using lambda and an arrow to mean a lambda abstraction, this ampersand to mean application, and bang to mean referring to a variable. And it is like the classical, like it is just the standard CPS translation. But notice in particular, in, for instance, the variable case, I'm not saying let's pick a name for the continuation which is not free or which is distinct from the variable or something. I'm just calling it k, the string k. And then whenever I need to refer to something which must be distinct from k, I just say, let's shift k in this term so that this term cannot possibly pick up any references to the k that we have. And this is more interesting maybe in the lambda case, where here the result of CPSing, so this is CPSing with the term which has been opened with the name x. It might well have free occurrences of x, but it's not supposed to refer to k. And that says, well, okay, that's fine. We just take whatever it was and we shift it by k. The interesting thing to prove about this is Mayer-Mon's theorem that CPS conversion preserves types, or at least you can take a typable term, transform its type in some double negation-y looking way, and the CPS conversion will have that type. So the proof is basically just apply the typing rules. Like, I mean, there's nothing particularly complicated going on here. But the interesting case is that lambda thing, where we had two names, x and k, in scope. And we end up trying to show that, we need to apply weakening because there's a variable k that doesn't appear in the original one. And what we end up doing is, if we just like simplify through, we end up seeing this piece of code. Is that legible over there? Oh.
Legible but not intelligible.
Yeah, sounds about right. So what's going on is here it's closing. So we're trying to show that everything that appears in the original context appears in the result context. So it's saying compare x and v. And if they're the same, then look in the rest of the context. Sorry, if they're different, look in the rest of the context. And if they're the same, it has to be the right type. And that should give the same answer as the other side. But the bit that I want to point out is here we're comparing x and shift k of v. And this is the point where, if you've been using the Bruijn indices to do everything, this is the point where you just break the pencil in half and give up in frustration, because you now need to do a big mess of arithmetic to swap two names. Whereas here, we can just say, actually, let's just swap those two names. Swapping a close and a shift, that's something that is going to require a side condition. The side condition that it requires is that the names are distinct. But since I got to actually choose those names, I didn't have to pick them. Then the thing that I have to prove as a side condition is that the string x and the string k are not in fact the same string, which is something that even Cock will admit is easy. So, that's it. Thank you. Yeah, so, I mean, that is true. If we were doing this inside a compiler, then if we took the naive definitions that we have here, we'd spend an awful lot of time walking back and over terms, shifting things and weakening things and pushing things up and down. And perhaps something more like explicit substitutions that was a bit lazier and only did the bit of rewriting that it needed to do would be an improvement. But we haven't really thought about how this should be used inside a compiler, but it probably shouldn't be just directly imported, because it would be too slow, rewriting everything all the time.
So you mentioned row being this banner structure of open and close and switch. Is there a nice inductive definition that you can show us?
Oh, sure. I'm sorry, this is of the balanced renamings?
I was thinking typing with the block is also fine.
Oh, I mean, they're defined as just a bit of syntax that is like a collection of nested renames, like renamings, shifts, and substitutions, and they apply them by walking over that syntax. There's nothing particularly deep going on here.
Okay, one more question while our speakers change out. So,
Yeah.
Again, back to computational complexity. So in terms of this big O notation, like open and close, like defining substitution in terms of open and close and all this stuff, does it have the same computational complexity as the older version that has the types under something without shifting names?
It has the same complexity as the older version if you actually evaluate the side condition and you walk over the term to work out what's free. In an actual implementation, what you usually do is cache which variables are free so that you don't have to look them up every time. And I think, and we're not doing that at the moment, and I think we should do something similar where we like lazily evaluate the substitutions. So at the moment it is worse, but I think it could be done something like that.